Imagine the biggest, loudest, most spectacular fireworks display you've ever seen. Now multiply that by 1,000,000,000. Then multiply that by another 1,000,000,000. You're still not even close to the cosmic spectacle we call a supernova. This isn't just a firecracker, it's the universe putting on its grandest show. It's a star, a massive, powerful star, ending its life in a blaze of glory. So bright it can outshine its entire galaxy. For a few brilliant weeks, a dying star can be brighter than hundreds of billions of stars combined. It's the ultimate go-out-with-a-bang moment, a final, breathtaking performance on the cosmic stage, and it's one of the most important events in the entire universe. This isn't just a distant, abstract light show. These explosions are fundamental to everything. The universe's ultimate recycling program. The very atoms that make up you, me, the Earth, your smartphone, were cooked up inside stars and blasted across space by supernovae. Let's break it down. What is a supernova? It's a star that explodes, but not just any star. We mean the heavyweights of the cosmos. Spectacular death of a very massive star, Type 2. Or sometimes a small, dense white dwarf in a binary system explodes, Type Ia. A star is a balancing act, gravity pulling in, fusion pressure pushing out. Nuclear fusion releases enormous energy that holds the star up for millions to billions of years. Eventually the fuel runs out and the balance fails. When fusion weakens, gravity wins. Collapse begins. That collapse can trigger a runaway that ends in a catastrophic explosion, a supernova. Next, we'll follow a star's life, and see why some die quietly and some die loudly. To understand why stars explode, first we must see how they live. Stars are born in giant cold clouds of gas and dust, stellar nurseries. Gravity gathers material into clumps. As they collapse, they heat up. Eventually the core reaches millions of degrees and nuclear fusion ignites. A star is born. Fusion pushes outward, balancing gravity. The star settles on the main sequence for most of its life. Our sun is in the main sequence now and will stay for about 5 billion more years. How a star ends depends on mass, how much material it was born with. Smaller stars sip fuel slowly, swell into red giants, and quietly leave behind white dwarfs. Massive stars, at least 8 times our sun, burn much hotter and live far shorter lives, a few million years. They fuse heavier elements in stages, helium to carbon, carbon to neon, neon to oxygen, and finally to silicon. The star forms onion-like layers of elements. This goes on until the core is mostly iron, the end of the line for fusion. And that iron core sets the stage for a dramatic ending, collapse and explosion next. Let's go deeper, to the heart of a dying star. The creation of an iron core is the beginning of the end for a massive star. It's the point of no return. Until now, fusion reactions released energy to support the star, but iron is different. Fusing iron requires energy instead of releasing it. Iron is cosmic ash. The core's furnace stalls. It no longer produces the outward pressure needed to resist gravity. Gravity has nothing left to fight against. The tug-of-war ends. In less than a second, the core collapses catastrophically. From the size of the Earth to a ball only a few dozen miles across, an almost unimaginable compression. The collapse reaches a quarter of the speed of light. The outer layers hang in inertia, unaware of the disaster inside. Protons and electrons are forced together into neutrons. The core becomes packed neutrons. This new, ultra-dense object is called a neutron star. The core hits maximum density and rebounds, like a rubber ball on concrete, sending a shockwave outward. A powerful shockwave races outward through the star. Collapse releases a flood of neutrinos that carry immense energy. They help power the outgoing shock. When the shock slams into the infalling layers, a detonation occurs. The star tears itself apart. What follows is one of the most powerful displays of energy in the universe, the supernova itself. Next, the explosion. The cosmic kaboom. The moment the shockwave hits the outer layers is when the supernova truly ignites. The explosion rips through the star's layers. Hydrogen, helium, carbon, oxygen, blasting them into space at incredible speeds. Speeds can reach up to 10% the speed of light. That expanding cloud of stellar guts is what we see as the supernova remnant. For weeks it can glow like 100 billion suns, a beacon visible across cosmological distances. But a supernova is also a cosmic factory, forging heavy elements in the heat and pressure of explosion. Gold, silver, platinum, uranium, formed or distributed by supernova. Every bit of gold in a wedding ring likely originated in the heart of an ancient supernova. Humanity has watched these cosmic fireworks for thousands of years. Ancient astronomers called them guest stars. The guest star of 1054, recorded in detail, left us the Crab Nebula we still study today. Tycho Brahe observed a supernova in 1572, a new star in Cassiopeia that challenged old ideas. Kepler saw another in 1604, the last clearly visible supernova in our galaxy to the naked eye. Statistically, we expect about 1 or 2 per century in the Milky Way. Some may be hidden behind dust. The most recent naked-eye example was SN 1987A in the Large Magellanic Cloud. For the first time, modern telescopes and detectors let astronomers study a nearby supernova in detail. We detected neutrinos before the light arrived and have watched SN 1987A evolve for decades, a gift to science. These events are cosmic laboratories, revealing how stars die and how elements form. So what happens after the smoke clears? An expanding cloud of gas, a supernova remnant, drifts into space. For many Type II supernovae, the core becomes a neutron star, unimaginably dense and small. Imagine 1.5 times the sun crushed into a 12-mile sphere. A teaspoon would weigh millions of tons. Some spin rapidly and emit beams, pulsars, like cosmic lighthouses detected by radio telescopes. If the core mass exceeds about 3 solar masses, gravity wins completely and a black hole forms. The expanding remnant, like the Crab Nebula, is one of the sky's most beautiful sights, cooling and evolving for thousands of years. By studying remnants and central objects, we piece together the star's final moments, cosmic forensics at work. Supernovae are not just destruction, they are acts of creation. They are the reason we exist. Think about the elements in your body: carbon, oxygen, nitrogen, calcium, iron. Hydrogen and helium come from the Big Bang. Everything else was cooked in stars. Massive stars fuse elements up the ladder: iron, nickel, silicon, magnesium, layer by layer inside the star. The explosion itself forges the heaviest elements: gold, platinum, uranium. Blast waves distribute metals into space. Over millions of years, the enriched gas cools and forms new star-forming clouds. Those clouds collapse to make a new generation of stars and planets, richer in heavy elements. Iron in your blood, calcium in your bones, all from stars that died long ago. We are literally made of stardust, or more precisely, supernova dust. The next time you look up at the night sky, think about what you're really seeing. Not just lights, but a vast, dynamic, and sometimes violent universe. You're looking at cosmic forges that created the ground beneath your feet and the air you breathe. With ground and space telescopes and detectors for gravitational waves and neutrinos, we study supernovae more deeply than ever. We detect ripples in space-time and ghostly neutrinos, echoes of stellar death. We watch remnants evolve and piece together how these engines shape galaxies. Supernovae help shape galaxy evolution and seed the materials for planets and possibly life. Stars die so that new stars and worlds can be born. A cosmic recycling that leads to us. It's the greatest show in the universe, and we all have a front row seat. Be curious. Keep looking up. The tickets are free. All you have to do is look.